In this presentation, we talk about what happens when you connect a capacitor to an AC voltage supply, and we're going to also talk about the impedance for a capacitor. So for a purely capacitive circuit, if you connect that capacitor to a voltage supply, it turns out that the voltage and the current are not in phase with one another, and in fact the current leads the voltage by 90 degrees. So if we think back to capacitors that are connected to a DC voltage supply where there's a switch involved and a resistor, let's say, and the capacitor is initially uncharged. If it's uncharged, that means it doesn't have any voltage on it. So when you close the switch, the current immediately starts to flow on that capacitor. So there's a large amount of current to start with and no voltage. And then as time goes on, eventually the capacitor reaches steady state with the DC voltage supply. And at steady state, the voltage has built all the way up so that it has its maximum voltage and the current has dropped down to zero. So if you think about how capacitors work for DC, similar to inductors, it makes sense that the voltage would lag behind the current, or that the current would lead the voltage, because that capacitor is initially uncharged and the current would jump right up to start charging that capacitor, and it takes time for the voltage to build up across that capacitor. So if we assume that the voltage across a capacitor is varying sinusoidally with an amplitude of Vm, then our goal is to try to write down an expression for what the current would be that passes through that capacitor given the voltage. So we know that the charge on a capacitor as a function of time depends on the capacitance and the voltage across the capacitor. So if we go back to our definition of current, where current is just the rate of change of charge in the circuit, and we plug in this value for the charge as the voltage, the capacitance times the voltage, then the current that passes through a capacitor or is near the capacitor on the plates is just the capacitance times the rate of change, or the derivative of the voltage across the capacitor as a function of time. So we want to take the voltage that we have across that capacitor and we want to take the derivative. And so when we take the derivative of sine, and the voltage of course is a constant, I could pull that out, but the derivative of sine is a cosine. I can pull all of the terms that are constants out front. When I take the derivative of sine, I get the cosine, but then I have to also take the derivative of what's inside. And when I take the derivative of what's inside, that factors out another omega, or an angular frequency. That's where that comes from. So all of the terms that are in front of the cosine can be replaced with the amplitude of the current. In other words, I want to write the current as having some maximum current, and then I'd like to write it times sine of some angle in order to write it as a sinusoidal varying function. So I know that sine and cosine are related to one another, so I'm going to take this cosine function and I'm going to convert it into sine, because cosine is just sine plus 90 degrees. And then all those terms that are out in front of the sinusoidal function are just the maximum current, or the amplitude of the current through the capacitor. So the current, the maximum current can be written as the capacitance times the angular frequency times the voltage. Well, if you remember, we had Ohm's law for resistors, V equals IR, and then we had the equivalent of Ohm's law for an inductor, and for an inductor, it was the voltage is equal to the impedance times the current. And so we'd like to do something similar to that here. If I divide both sides of this expression that's relating the maximum current to the maximum voltage by the capacitance and the angular frequency, I get that the voltage is equal to the current times the fraction of 1 over the capacitance times the angular frequency. So this looks similar to V equals I and then R, right, here, which would be in parentheses. But instead of it being the resistance, we say that it has capacitive reactance. And the capacitive reactance is just this term that's in parentheses right here. And it's the ratio, it's 1 over the angular frequency times the capacitance. So what is capacitive reactance? So capacitive reactance is similar to inductive reactance. It's a measure of how much the capacitor is resisting the flow of current in the circuit. So the bigger the capacitive reactance, the larger the resistance is to the flow of current in that part of the circuit where the capacitor is located. In terms of units, capacitive reactance also needs to have units of ohms, because this looks like Ohm's law, V equals IR, and this term would have to have those same units. You'll get the units of ohms if our capacitance is measured in farads and our angular frequency is measured in radians per second. So we end up with a current through the capacitor that is leading by 90 degrees the voltage across that capacitor. Going back through and just looking at our definition of current through a capacitor as it relates to the voltage. So if we were to draw a picture of this in terms of the waveforms, I would draw the voltage across the capacitor as a sinusoidal function, and I would draw the current as being shifted by 90 degrees to the left. So the current reaches its maximum first, and then the voltage. In phasor notation, this shows us that the current is at an angle of 90 degrees. The voltage is on the axis, and the current is leading the voltage. It's ahead by a factor of 90 degrees. So a little bit more on this capacitive reactance. So again, we can always sort of think about this in terms of Ohm's law. So if this was resistance, it would be voltage over current, but instead of resistance, it's this capacitive reactance. Which is just 1 over the angular frequency times the capacitance. It's measuring how does that component, in terms of a capacitor, oppose the current that's flowing through the circuit. As I mentioned earlier, the angular frequency needs to be in radians per second. The capacitance needs to be in farads, and under those conditions, the capacitive reactance will be in units of ohms. So we could summarize this in terms of a purely capacitance circuit. And if we only have a capacitor in the circuit, we could use the equivalent of Ohm's law to figure out what is that capacitive reactance. Or more specifically, we could figure out the maximum voltage in that sinusoidal varying voltage supply by taking the maximum current times the reactance, the capacitive reactance. Or we could rearrange that like we would for Ohm's law, take the voltage over the reactance and get the current, and so on. Let's consider an example of a capacitor that is connected to a voltage supply that's oscillating with respect to time. So we have a 10 microfarad capacitor, and we know that the voltage across that capacitor is 100 volts times sine omega t minus 40 degrees. And the frequency of oscillation is 1,000 hertz. And our goal is to determine what is the current that is passing through that capacitor as a function of time. We know that in a capacitor, the current leads the voltage by 90 degrees. So that means that we can write the current as having some maximum value times sine omega t minus 40. Plus, I have to add to that a phase angle of 90 degrees because the current leads by 90. So in order to continue, I need to figure out what is that maximum current that would be passing through that capacitor. And in order to find that maximum current, I know that I need to have the capacitive reactance. And the capacitive reactance is just 1 over the angular frequency times the capacitance. In this case, I don't know the angular frequency. I know the actual frequency is 1,000, and the angular frequency is 2 pi times the frequency. So I can plug in those values 2 pi times 1,000 multiplied by the capacitance, which is 10 microfarads, so that's 10 times 10 to the minus 6. And I take those values, multiply them, and then 1 divided by that, I get 15.9 ohms. Using the capacitive reactance, I can figure out what the maximum current is in my sinusoidal varying supply, or my sinusoidal varying current, by taking the maximum voltage, which is 100 volts, and dividing by that capacitive reactance. So 100 divided by 15.9 gives me 6.28 amps. So the current that goes through my capacitor as a function of time has a maximum value of 6.28 amps, and it has its phase shifted to the right, or its phase shifted to the right, an angle of 50 degrees, which is off and leads by 90 degrees from the voltage supply. So if I were to make a plot of these values, I could plot the voltage as a function of time in terms of the waveform. It's shifted to the left by 40 degrees. Excuse me, it's shifted to the right. The negative sign is shifted to the right. So I have my voltage supply here. And my current supply was 6.28 amps, and it was shifted to the left by 50 degrees. So the current leads by at an angle of 50 degrees. The voltage supply lags behind, and it's at an angle of 40 degrees. So the current is actually leading the voltage by an angle of 90 degrees. So if you have a purely capacitive component, the current will always lead the voltage by 90 degrees. If we were to make a plot of the capacitive reactance versus the frequency, we would see that there's an inverse relationship. So the capacitive reactance is inversely related to the frequency, and it's inversely related to the capacitance. So what does that mean? So let's think about the capacitance. If a device has a really large capacitance, that means it has a large ability to hold charge, which means that it's going to be kind of hard to fill it up, right? So if you have a large capacitor, you're going to have a small capacitive reactance, a small resistance to the flow of electricity, because it's very easy to put charge onto that capacitor, and in fact, if it had a lot of charge on it, it would be plenty to take off of it. So it's not like your capacitor is going to fully charge and cause there to be some resistance. So the fact that the capacitive reactance is inversely proportional to the capacitance makes sense. It also makes sense in terms of the frequency. So if you have a large frequency of oscillation, the capacitive reactance is actually small, right? They're inversely related to one another. Large frequency, small capacitive reactance. So if you have a large frequency, that means that your source is oscillating very quickly, and all that means is that that capacitor can charge and discharge very easily. It's not going to fill up very quickly because you're always putting charge on and taking it back off again. And so the fact that there's an inverse relationship there actually makes sense. Versus as the frequency goes towards 0 over here, that means the capacitive reactance gets really big. So if the frequency goes to 0, that means your capacitor is just charging and charging, and eventually it's almost like DC, right? So the capacitor will just charge up, and then it'll act like an open circuit again. So this relationship actually makes a lot of sense in terms of what we know about DC and just transient current and voltage when you have inductors and capacitors. So similar to our discussion about impedance for resistors and inductors, we can also define the impedance for a capacitor. So impedance is always defined as the voltage over the current. And so this is just sort of a reference to what we had talked about before. This is the equivalent of Ohm's law for AC. And we talked about the fact that a component that has impedance can have impedance that is a combination of resistance, it could be inductance, and it could be capacitance, and it can be combinations of all of those different things. So in general, when we're talking about impedance, we're always going to use phasor notation, and we're going to treat it as a complex number when we're thinking about it. If I want to know what the magnitude of that impedance is, I can always take the voltage that passes, the voltage across that component, the maximum value, divide by the maximum current, and that will tell me the magnitude of the impedance. And then how the voltage is related to the current in terms of how they are shifted from one another will tell me the angle for the impedance. So let's think about impedance values for if I have a purely capacitive or capacitance in my circuit. So we know that the current leads the voltage by 90 degrees, and so if I have a voltage that has a zero phase shift, that means that my current through that capacitor is leading by 90 degrees. If I want to know what the capacitive reactance is, I could write the voltage and the current in phasor notation. The voltage across the capacitor would have some amplitude, so here I wrote Vc instead of Vm, and the angle here is 0 degrees. The current through the capacitor would have some amplitude, which I wrote as Ic, and it would be Im here, and it has a phase shift of plus 90 degrees. If I take the voltage and I divide by the current of the capacitor, just their amplitudes, that gives me the reactance of the capacitor. So the impedance is just the reactance. What is the resistance of that component to the flow of electricity? And it has a phase angle of 0 minus 90, so negative 90. So it does not have a real part, and its imaginary part is negative. So if you're thinking about comparing capacitors and inductors, they both have imaginary parts in terms of their impedance. One has a positive 90, that would be the inductor, and the capacitor acts opposite that and has a negative complex part. And remember that reactance for a capacitor over here is just 1 over the angular frequency times the capacitance. So let's see if we can work a problem now that has, similar to the last problem that we looked at, but doing this in terms of phasor notation. So I have a circuit. I'm going to use this phasor algebra to find the voltage across this capacitor, and then I'm going to sketch those phasors and the waveforms. So I'm given that the current that is passing through this capacitor is 5 milliamps times sine omega t plus 120, so the current has a phase angle of 120. I'm given that the angular frequency is 1,000 radians per second and that my capacitor is a 0.1 microfarad capacitor. So the first thing I'm going to do, since I'm using phasor notation, is I'm going to write my current through the capacitor in phasor notation. So I need to use the effective value in phasor notation, so 5 milliamps over the square root of 2. Gives me 3.54 milliamps, and then the angle, the phase shift is 120 degrees. Next, I'm going to be interested in writing the impedance for the capacitor, and in order to write the impedance for the capacitor, I have to know the reactance for the capacitor. So the capacitive reactance is 1 over the angular frequency times the capacitance. This is 1,000 radians per second times 0.1 times 10 to the minus 6 farads, so I have to convert my microfarads into farads. I multiply those values. 1 divided by that quantity gives me 10,000 ohms. So again, as long as I have radians per second and I have my capacitance in farads, there should be a farad here, then I will get my capacitive reactance in ohms. Since I'm using milliamps here, it makes sense to take that ohms and convert it into kiloohms, so my capacitive reactance is 10 kiloohms. I often do a lot of cutting and pasting, and so I noticed on here that I forgot to change this. This should not be an L, this should be a capacitive reactance right here, not inductive reactance, so I apologize for that. Once I know what the capacitive reactance is, I can determine the impedance for that capacitor, and it's just the capacitive reactance with a phase angle of -90. So I would take my 10 kiloohms and I would put that with a phase angle of 90. So my capacitive impedance is a negative imaginary part of 10 kiloohms. Once I know what the capacitive reactance is and I know what the impedance is, I can use the equivalent of Ohm's law, and I know that the voltage across the capacitor is the current through the capacitor times the impedance of the capacitor, where these are all phasors. I know what the current is because I'm given that value. I know what the impedance is for the capacitor. I can multiply those quantities together, so 30 kiloohms times 3.54 milliamps is going to give me 35.4 volts. And when I multiply, I would add the angles together, so 120 plus a -90 gives me 30 degrees. So the voltage across the capacitor in phasor notation is 35.4 at an angle of 30 degrees. I can rewrite that in terms of waveform notation or the sinusoidal form. If I write it back in sinusoidal form, I want to have it as the maximum value, so I would take the effective value and multiply by the square root of 2. And then that would be sine omega t plus my phase shift of 30 degrees. And if I multiply the square root of 2 times 35.4, I get 50. So I have 50 volts sine omega t plus 30. So the current was leading. It had a phase angle, phase shift of 120, and the voltage had a phase shift of 30, so the current is leading by 90 degrees. If I were to draw a picture of this, I could draw the sinusoidal varying function where my voltage supply is shifted to the left by 30 degrees. My current supply here is shifted to the left by 120. And if I draw them in phasor notation, I have my current supply is at 120, my voltage is at 30, and they are shifted from one another by 90 degrees. So when I have a capacitor and I look at the current that's flowing through that capacitor versus the voltage across the capacitor, that current is always going to lead the voltage by 90 degrees. And I realize some of these are sort of easier examples, but we need to understand the basics of how to use impedance for individual terms so that we can then combine them together and understand how to do more complicated problems.